So I just will write the equations that are important from this chapter only. And we start with Ohm's law, which says that the voltage across some resistor R is proportional to the current that flows through that resistor. After that, we had three equations for power dissipated in some circuit element with resistance. So we said that the power is voltage times current, or it is current squared times resistance, or it is voltage squared divided by resistance. Similar formulas work for average power in the case of AC circuit. You just have to substitute the voltage and the current with the RMS values. So I'm not going to write the same formulas. You just keep that in mind. We also talked about capacitors and resistors connected in parallel or in series. So resistors connected in series give you an effective resistance equal to the sum of the individual resistances. While resistors connected in parallel, have equivalent resistance given by the following expression. The inverse of the equivalent resistance for resistors connected in parallel is equal to the sum of the inverses. So, and this formula for the case of only two resistors connected in parallel simplifies to R parallel is equal to the ratio of the product divided by the sum. R1 plus R2, right? R1 plus R2. Capacitors connected in series in parallel behave in a way opposite to the resistors. In other words, capacitors connected in series give you equivalent capacitance that has an inverse equal to the sum of the inverses. And again, for the case of two capacitors connected in series, you can say that capacitance, equivalent capacitance is product divided by the sum. So what you have to also keep in mind is that when you have capacitors connected in series, they must carry the same charge on their plates, no matter if they are the same capacitance or different capacitance. If they are connected in series, the charge from the first one should be equal to the charge from the second one, should be equal to the charge on the plates of the third one, and so on. Capacitors connected in parallel give equivalent capacitance equal to the sum of the individual capacitances. A formula that is useful for figuring out conceptual questions and also solving problems is a formula which defines capacitance. So capacitance is the coefficient of proportionality between the charge on the plates and the voltage difference between the plates. So this coefficient of proportionality is what we call capacitance of the system of two plates or two metal objects in general. After that, we had the tools to solve circuits that include multiple resistors and batteries connected in different ways. Those rules, well, we figured out how to analyze circuits of that type by applying the Kirchhoff rules, the junction rule and the loop rule. And you just have to go to the checklist that we wrote last time, and you have to exercise how to do that. And what is left from this chapter is a little bit of discussion about how a circuit that contains a battery, capacitor, and resistor connected in series, how does this circuit behave? So let's say here is a circuit, here is the resistor with resistance R, here is a capacitor with capacitance C, and let's say that you have, you may have some switch that closes the circuit like this, and maybe a battery with voltage V. So how a circuit like this behave? And well, it can be shown that the presence of the resistance makes the capacitor charge gradually and reach some maximum value of the charge on the plates of this capacitor. And the formula describing the charge on the plates of this capacitor as a function of time looks like this. Q naught times 1 minus exponent to power negative t divided by the product of the resistance times the capacitance. So if you analyze, so this formula is not derived in the textbook, but the derivation is not that difficult, but it uses some differential equations which we cannot solve with the tools that we have, with the algebraic tools. But look, if you draw a graph representing the function given with this equation, so the horizontal axis is time, the vertical axis is the charge as a function of time, and Q naught is somewhere here. The function looks like an exponentially increasing function that reaches a maximum value equal to Q naught. So the asymptotic value of the charge on the plates of this capacitor is equal to Q naught. And you can see that just by looking at the exponent. So when the time t goes to infinity, the exponent becomes equal to 0, the expression in the brackets becomes equal to 1, and the value of the charge becomes Q naught. So the physical interpretation of this formula is not so difficult to figure out. Let's say that you close the circuit by closing the switch, and the initial, let's say, positive charge that is moving from the battery to this plate of the capacitor is going to have easy time reaching the plate. The following positive charges that are moving in the same direction are going to have harder time because there are already positive charges on this plate, and those positive charges are going to repel the new charges, the newcomers. So the speed with which the new charges are going to arrive is going to slow down, slow down, slow down, and eventually no more charges are going to be able to pile up on that plate of the capacitor. So this is how you look at this situation. The product of resistance times capacitance is called time constant, and it has units of time, seconds, measured in seconds. And you just, that time constant just tells you what is the scale, what is the time scale of charging and discharging of this capacitor. Now, if you start with a charged capacitor, so if you start with the capacitor, you have a resistor again, and you have a capacitor that is already charged with charge Q naught. This means Q naught charge on the positive plate, negative Q naught on the negative plate. So this is the circuit that you have. Again, you have a switch, but you don't have a battery anymore. You have a situation like this. No battery, but you start with a charged capacitor. Close the switch and look, all those charges that are on one of the plates, let's say on the positive plates, they repel each other. They want to get away from each other, and very fast, those positive charges are going to flow in counterclockwise direction once you close the circuit. Go and reach the negative plate and neutralize some negative charges. Again, initially, those charges are going to flow very fast because there are many charges piled up on the plate. So they're going to repel each other stronger, and you're going to see a very fast movement of charges in counterclockwise direction, positive charges in counterclockwise direction. Well, the equation that describes the amount of charge on the plate of the capacitor as a function of time is going to be an exponentially falling function, exactly with the same time constant like in the previous case. And graphically, that function looks like this. So time, the charge on top of the plates, and you're going to start with some charge Q naught right here, the maximum value, and that charge is going to exponentially drop and reach 0. The exponential drop is going to be with the same time constant, with the same scale, time scale, as in the previous case. Okay, let's see questions and remarks here. Yes.
So basically, they'll just, when you close a switch, they'll go to the positive side, and then once it gets there, it'll start going back down to the negative side or back to the positive side.
So you start with a charged capacitor, many positive charges here, and exactly the same number of negative charges on the other plate. You close the switch, and those positive charges are able to go around the circuit and start neutralizing the negative charges on the other plate.
Okay.
So they're just going to, well, many of you are taking the lab, you're working with capacitors there. If you take a large capacitor, with large capacitance, you charge it with a battery and you leave it on the desk. It is going to stay charged for a long time. The only discharge is going to happen because of the presence of ions in the air. And this discharging may take very long time. So if somebody grabs this charged capacitor and touches the two terminals, the two plates of the capacitor, well, in that case, the body of the person is like the resistance here, and the capacitor is going to discharge through the body of the person that holds the two terminals. And this person is going to feel it, right? So don't do this to your classmates, but keep in mind that if you open any electronic device, especially devices that contain large capacitors, like electric motors, for example, even if your device is disconnected from the grid, the capacitors that are in it may be charged. And if you open it and you're not careful, you may get unpleasant surprise. So just because you may discharge a capacitor through your body.
Somebody asked what the that equation represents with the cursive T, and then what the S in the bracket
This one?
means. Yep.
This is a definition for a time constant, and this letter is the Greek letter tau. Standard notation for a time constant, but you can use any notation you prefer. So this is the definition for time constant, tau. Yes?
Is there a reason why the bottom diagram you drew doesn't have a battery?
If you have a battery connected to this circuit, this capacitor is not going to discharge. So you're going to have this situation, like the previous situation. Charged capacitor, it is going to stay charged forever.
Okay.
So you have to remove the battery in order to see change, in order to see the drop, the discharge of this capacitor. Okay, other remarks?
Yeah, they were wondering what the S in the brackets.
Seconds. Units for the time constant is the units for time, SI units, seconds. Okay. So knowing this, let's answer problem number 13 from the homework assignment. And if I don't forget, I promised to leave a problem similar to problem number 13 for the midterm test on Friday. So remember that on Friday this week, we have a test scheduled, and people that are registered for the in-person class are invited to take the test from 11 o'clock if you can, if this is possible. If not, just you have to let me know, and we're going to arrange something for you. And people that are registered for the online class are going to have the test at 1 o'clock online via Zoom, and I'm going to email them the questions and with instructions how to handle the test. So let's solve now problem number 13 from the homework assignment, and I think that I have that problem on the web browser. It is just find one of the so problem number 13. Yeah. So again, a problem similar to problem 13 you may encounter in the test on Friday. So in this problem, you have RC circuit. Of this type right here. So this is problem number 13. Here's the circuit that we're analyzing. They say that the time constant of this circuit is 2.8 seconds. For my version, for your version, it is going to be a different number, of course. In other words, tau equals to RC is equal to 2.8 seconds for my version. How much time is required for the capacitor that is initially not charged to gain half of its full charge, full equilibrium charge like this? And look, to answer this question, you just directly apply the formula that describes the charging of a capacitor. Directly this formula. So you want at the final moment of consideration the charge Q to be equal to half of Q naught. Q naught is the maximum value. You want 1/2. In other words, you have this 1/2 of Q naught is equal to Q naught times 1 minus e to negative t over RC, where RC again is equal to 2.8 seconds. And this is your equation. And now look, the maximum charge Q naught cancels out, and you have one single equation with a single unknown, the time. The value of the product RC is given, 2.8 seconds. So you just have to rewrite this equation and solve it. It is not a polynomial equation. It has an exponent, but you know how to handle equations with exponents. So let's do it. So you have this. 1/2 is equal to 1 minus e to negative t over RC, right? This is what you have. You move this 1 to the other side of the equation with opposite sign. So you're going to have 1/2 minus 1 is minus 1/2. And on the other side, you're left with negative e to power negative t over RC, right? This is what you're left. You can multiply both sides by -1 to get rid of the negative algebraic signs. And after that, how do you handle an equation like this? You take logarithm of both sides, natural logarithm. So you have natural logarithm of 1/2 should be equal to natural logarithm of exponent to negative t over RC. But you know that natural logarithm of exponent is equal to the power of this exponent. And you're going to get logarithm of 1/2 is equal to negative t over RC. And now solving for time, you get that time is equal to negative RC multiplied by logarithm of 1/2. So this should be the answer.
Somebody asked why you divided the Q naught by 2 originally.
Why did I divide Q naught to 2? Because in the problem they say how much time is required to gain 1/2 of Q naught, 1/2 of the maximum charge. The maximum charge is Q naught, so 1/2 of it is Q naught divided by 2. So now look, you have a negative algebraic sign in the answer, but logarithm of 1/2 is a negative number. So the time is going to be a positive number, as it should be. Let's see questions and remarks. And let's see if yeah, well, before I solve a couple of more problems, let's talk a little bit about safety, because, well, safety is important when you work with electric circuits. So you have seen that sometimes electricians work without turning off the voltage, sometimes high voltage, sometimes 72,000 volts, and you see a person 30 feet above the ground fixing some high voltage line. So how do they do it? Well, you shouldn't try it yourself, but if your body is high resistance to currents, in other words, if you wear rubber boots and rubber gloves and you're on a ladder that is not metal ladder but made of some insulating material like fiberglass, you can safely touch a line that is under voltage. Remember that the voltage shouldn't exceed the value of something like 10 kilovolts per centimeter. Otherwise, you're going to experience certain unpleasant. So what is going? So the voltage itself doesn't harm you. What harms you is the current that would flow through your body. But you see that Ohm's law says that voltage and current are proportional to each other. Well, if the resistance of your body is high enough, the current that is going to flow through you is going to be zero and you're going to be safe. And you have seen that birds, especially in the spring and in the fall, they perch on high voltage lines and they are doing no problem whatsoever. Why? Because no current can flow through their body. They are touching high potential, but the current cannot flow through the air that is around them. And no current is going through them, and it is perfectly safe. However, if a bird spreads its wings and touches one line with one wing and the other line, different line with under different potential, different voltage, with the other wing, a current is going to flow through this bird and the results are not going to be good. So the rule is that, yeah, well, fried chicken, yes. So the rule is that a current of the order of 1 milliamp, 1,000th of an amp, is okay. You're going to feel it, but it is not going to create any negative health effects if it is for short time, of course. A current that is 10 times stronger, meaning a current of the order of 1/100th of an amp, you're going to feel it very well, and actually you may experience uncontrolled muscle spasms. So in other words, if you touch, let's say, 120 volts like this, and the current of the order of 1/100th of an amp flow through your body, your muscle may contract, and you can grasp this voltage even stronger, and you're going to have the current flowing through your body for longer time. So don't do that. So sometimes, and again, I would advise nobody to do it, sometimes people check if voltage is present this way. Because if the muscle contracts, you're separating from the source and but don't do it. It is better to check the presence of voltage with a tool rather than with your hand. And if the current that flows through your body is of the order of 1/10 of an amp, you're going to experience substantial health effects like cardiac arrest and death. So this is something that you should avoid. This is not something that's good. Okay, so the power outlet on the wall looks like this. The standard power outlet on the wall looks like this. You have one longer terminal, one shorter terminal, and you have a hole like this. You have 3 terminals. The standard way to connect those terminals is this one is connected to the ground. This is for safety. So it is at 0 potential. The long one also has to be connected to the ground if it is connected correctly. But don't count on it, because the electrician that wired this outlet may have made a mistake. So you shouldn't count that this one is under 0 potential. Well, this terminal is connected to a voltage V equal to V naught times sine of 2 pi ft. In other words, it is AC voltage with amplitude V naught equal to about 170 volts. RMS value of this voltage is about 120 volts. Now, you know that some appliances in your house are connected to 240. Potential difference of 240. Like the dryer, for example, is usually at 240. So how do they work? So a 240 outlet looks like this. You have 2 terminals like this. Of course, you have, for safety, you have the grounded. You should have the grounded for safety. Now, this terminal is connected to V equals to V naught times sine of 2 pi ft. The frequency is always 60 hertz here for the United States. And this terminal is also connected to the same type of voltage, but it is shifted by 120 degrees. It is shifted by 1/3 of a cycle. So this is V prime equal to V naught times sine of 2 pi ft plus 120 degrees, let's say. So what does this mean? This means that if one of the terminals, the voltage changes like this, V as a function of time looks like a standard sine function like this. The other terminal provides exactly the same sine function, but shifted by 120 degrees. So this is one cycle. 1/3 of this cycle is 120 degrees. So 1/3 is about here. Maybe here, like this. And therefore, the second voltage looks like, well, like this. And using, well, I cannot make it exactly accurately, but you can imagine how it works. The red is shifted. So this one is the red. It is shifted by 1/3 of a cycle. And if you use trigonometric identities, you're going to see that the difference between V and V prime is going to be another sine function with the same frequency, but double the amplitude. So the RMS value of this voltage is going to be 240 volts.
Somebody asked, why does lightning not always kill an individual where it is on average 30,000 amps?
Actually, the voltage in that generates lightning can be much more than 30,000 volts per centimeter. Sometimes the total current and the voltage difference between the cloud that generates, let's say, the cloud from which the lightning comes and the ground, it could be sometime of the order of millions of volts potential difference, which means that you're going to have high voltage is going to have high current. Well, why doesn't it kill you? Well, I can say that probably not all of this current is flowing through your body. Some of that current may flow through a different path. And of course, if you're going to the right church, this is always. But you better don't count on it. But just make sure that when there is a lightning outside, you're inside the house or inside the vehicle, and it gives you protection, full protection. Okay. Other questions and remarks? So we have to talk a little bit about measurement of voltage and current, but we can do it as we discuss some of the homework questions. Let's go to problem number 11 from the homework assignment. Let's do problem number 11. Oh, it is exactly measurement. Okay. So in problem number 11, you have different possibilities for measuring the voltage and the current. And you want to measure the voltage and the current through a resistor R2. What is the right way to do the connection? So look, the voltage, the voltmeter measures the different heights of 2 points. And in order to detect those two different heights, you have to touch those two different points that you want to measure. They are different heights, they are different potentials. In other words, the voltmeter has to be connected in parallel, and parallel connection, for example, of the voltmeter is here, parallel to R2. Now, you don't want the voltmeter itself to affect the circuit substantially, to change the voltage to, that it is measuring substantially. And the way to do it is not to have any current or to have infinitely small current flowing through the voltmeter itself. So a good voltmeter has to have very high resistance, not to allow current to flow through it, and it has to be connected in parallel to the device across which you want to measure the voltage. The current, to measure the current, you think in a different way. In order to measure something, it has to go through the measuring device. This means that the ammeter, the current meter, has to be connected in series with the device to which you want to measure the current. And series connection of ammeter is only on circuit number, well, let's see, voltmeter is connected, okay. Yeah, so the first connection is perfectly fine because whatever current flows through the circuit, exactly the same current also going to flow through R2. So the first connection, the first diagram is accurate wiring of the measuring devices. The second one is not, because the voltmeter has to be in parallel with R2 and ammeter has to be in series with R2, and here it is in opposite way. The third connection is also meaningless. By the way, a good ammeter has to have infinitely small resistance in order not to affect the current that it's measuring. The current has to flow through this ammeter without much resistance. Yeah.
So if you're measuring the current that goes through R2, why is A okay? Because it goes through R1 before it gets to R2. It's currently measuring it before.
So what? Look, remember that the current, the electric current, doesn't get tired. It is exactly the same current flowing everywhere in this circuit. Remember, no current is going to go through the voltmeter because the voltmeter is infinitely high resistance. So look, it is a closed circuit and the same current has to flow through every single device connected in series. Yeah.
If B had the VM and AM switched, would it be accurate or no?
If VM and AM were switched in the second circuit, it would be perfectly fine.
Okay.
So you can put the ammeter here or here or here or here. Everywhere the current is the same, it is going to measure exactly the same current. But those are good questions. Keep asking questions like this. This is the only way to make sense of those circuits. Okay, other questions there? No? Let's go to problem number 17, maybe. Let's see what's problem 17. Okay. So problem 17. The easiest way to solve problem 17 is to use Kirchhoff rules. So let's solve. You can, since problem 17 has a single battery, that problem also can be solved without using Kirchhoff rules, but it is faster and easier to do it using Kirchhoff rules. So let's do it. So here's the circuit. One resistor here. You have a system of resistors like this. And another branch here and here. And all of this connected to a battery like this. Let's put the numbers here. So for my version, R1 is 3 ohms. So I'll write it 3 ohms. R2 is 5. R2 is here and it is 5. And after that, I have 2 and 1, 2 ohms, 1 ohm, and the last one is also 1 ohm. The battery is giving me a voltage of 18, for my version, 18 volts. They're asking us to figure out what is the power supplied to the 5 ohm resistor, to this one. What is the power supplied to this resistor? And look, to figure out the power, probably the best thing would be to say that the power supplied to the 5 ohm resistor is equal to the current that flows through that resistor, and I'll call this current I2 squared multiplied by the value of that resistance. This probably is the easiest way to. So this means that I'm calling the current that flows in this branch of the circuit I2. And let's start applying Kirchhoff rules according to the checklist that we had last time. So I'm saying, let's say that the current that is coming from the battery is current I call it I assign arbitrary direction to it. And that current I is flowing until it reaches the junction point. At the junction point, it splits into a current I2 and a current I1. Again, I put arbitrary directions to those currents. So this means that in this branch, I have current I1. In this branch, I have current I2. And eventually, when those two currents, so I1 is still here and here, and I2, of course, is here. And when they merge at the other junction point, they form the current I. Right? I intentionally put multiple notations for the currents, so you to realize that every branch, the current is exactly the same. The electrons, the current charges, electric charges don't get tired as they pass through a resistor. The second step in our checklist is put polarity across every single circuit element according to the direction of current flow. So current always has to flow from high to low potential. So I have plus minus here, and plus minus here, and plus minus here, and plus minus here, and plus minus here. And of course, the battery is the way it is connected. The battery, the longer terminal is positive, and shorter terminal is negative potential. So this is step number 2. The next step is apply the junction rule for one of the junctions. Here is one junction. The junction rule says that the sum of the incoming to the junction currents should be equal to the sum of the outgoing from the junction currents. In my case, the only incoming current is I, and the outgoing currents are I1 and I2. So this is my first equation. The second equation is going to come from applying the loop rule for one of the 3 loops that are present in the circuit. So let's maybe use this loop right here and start from arbitrary point on this loop. The rule is that the sum of the potential drops should be equal to the sum of the potential rises. So once I start from this point and start going, let's say, in clockwise direction, the first potential difference that I am going to encounter is across the 2 ohm resistor. And that potential difference is going to be equal to 2 ohms multiplied by the current I1, because voltage is current times resistance. After that, I keep going, I encounter the 1 ohm resistor, and it is again a potential drop. the value of that potential drop is 1 multiplied by I1. And this factor of 1, I can always skip. After that, I keep going. Again, I encounter 1 ohm resistor. But now I go, since I'm going clockwise, I go from minus to plus. This is a potential rise, and it has to go to the other side of the equation. In other words, I'll write it as 1 ohm multiplied by the current there is I2. And the final resistor that I encounter is 5 ohms. Again, I go clockwise from minus to plus. This is a rise. It has to go to the side of the rises. And the value of that rise is going to be 5 times I2. And finally, I'm back to the point that I started. So this is my second equation. Well, I have 3 unknown currents. I need one more equation, which is going to come by applying the loop rule for another loop. And you have a choice. You can use either this loop or you can use this loop. And the class is over. You're free to leave. If you want to stay, I'm going to finish this problem. If you have to go, please feel free. So which loop should I do the next equation? Which one?
The larger loop.
Okay, let's do the large loop. Let's say start from here. I go through the 3 ohm resistor, and it is going to be a potential drop. So right, the potential drop is going to have value 3 times I. After that, I encounter the 2 ohm resistor with another potential drop with value of 2 times I1. I keep going clockwise. That 1 ohm resistor is going to give me a potential drop with value of I1. I keep going. I encounter the battery. And since I'm going clockwise, I'm going to see a potential rise. So it has to go to the other side of the equation, a potential rise of 18 volts for my version of the problem. And now I'm back to the point that I started. So the system of equations looks like this. So from this system of equations, I have to find the value of the current I2. And, well, how to do it? For example, if you start with the third equation says 3 times I plus 3 times I1 is equal to 18. Yes.
Sorry to ask a question, but do one of your equations always have to include the voltage of the battery in the system?
This problem I can solve, well, no matter which loop I choose, the second loop is always going to have the battery.
Say it wasn't the case, say you could do 2 loops that didn't include the battery. Do you need the voltage to make it work?
One of the equations always has to include the battery. Otherwise, look, you change the battery, you're going to get different current and different answer. So the battery, no matter if you work correctly, the battery always is going to enter in one of the equations, at least one of the equations. So dividing this last equation to 3, you get I plus I1 is equal to 6, which means that you can say that the current I is equal to 6 minus I1. Substitute that current here in the first equations, and you're going to get 6 minus I1 is equal to I1 plus I2, which means that if you rearrange this equation, you're going to get negative 2 times I1 is equal to I2 minus 6. And dividing this equation to negative 2, you're going to get I1 is equal to 6 minus I2 divided, all of it divided to 2. The negative sign, I just changed the order in denominator, in nominator. And now this last expression allows me to substitute in the second equation of my system and solve for I2. So let's do it. So, well, let's first rewrite the second equation as 3 times I1 is equal to 6 times I2. And now substitute I1 with its equal, and you're going to, well, before doing that, let's cancel this 3. So you have I1 is equal to 2 times I2. Substitute I1 with its equal, and you're going to get 6 minus I2, all of this divided by 2 is equal to 2 times I2. Rewrite this as 6 minus I2 is equal to 4 times I2. Put the things on one side of the equation, and you're going to get 6 is equal to 5 times I2. And therefore, I2 is equal to 6 divided by 5. In other words, I2 is equal to 1.2 amperes. And once you know the current that flows through the resistor of 5 ohms, the power dissipated in this 5 ohm resistor is going to be I2 squared multiplied by the resistance. In other words, it is going to be equal to 1.2 squared multiplied by 5. And you have to see what this is. This should be 1.44 times 5 is going to give you 7.2. Exactly the answer. But, well, again, we followed a checklist. We didn't do much else. So I don't know. If you play around, I have to give at least one problem that requires Kirchhoff rules. If you write correctly the system of the linear system of equations, you're going to get 90% of the points for the problem. Solving is algebra. Yes.
So when I start with problem, I didn't use Kirchhoff's rules, where I lose points for that.
No, you're not going to lose problems, but you're going to, I'm going to give a problem where you have to use Kirchhoff rules. In this problem, it is possible to solve it without Kirchhoff rules, but you're going to have one problem where you have to use Kirchhoff rules. Yeah. Let me see, we have something on the chat. Yeah, you do. Okay. Okay, guys. So see you tomorrow at 11 if you can make it. You're welcome. Here in this room. And I'm going to broadcast on Zoom and also